And the last point, -1, 8. The y value again, we want to match up with a x value. We have a y value of 8, but the 8 we want to match up with a x value of 8. Since there are no 8's in the f function, this point does not map, or there is no composition for this point, so we'll leave this point off the answer, and our final answer will only be 3 points. 0, 0, 8, 3, and 3, 3. Title of the first section today, find the inverse of points. Definition for the section: to find the inverse, switch x and y. So if we have a point, we can switch the x and the y to find the inverse. First question, and only question for the section, 2, 6. Next point, 4, 5. And last point, -3, -1. Taking these 3 points, we can find the inverse by switching the x and the y. So the first point, 2, 6, the inverse by switching them around would be 6, 2. The second point, 5, 4. And the last point, -1, -3. So to find the inverse, the x and the y will switch, and the 3 points for the inverse, 6, 2, 5, 4, and -1, -3. Title of the next section is find the inverse of functions. In this section, we'll find the inverse of functions. 2 definitions, or 2 steps. The first step, switch x and y. And the second step, solve for y. So the same as the points, if we have a function, we can first switch the x and the y, and to have our final answer in y equals form, we can solve for y. First question, y equals -2x minus 1. To find the inverse again, the variable x and y, we can switch. So instead of y equals, we'll put a x in for y, so x equals -2, and instead of x, we can replace it with y minus 1. So we have x equals -2y minus 1. To write the inverse in y equals form, we can solve for y. To solve for y, we can add 1 on both sides. So we'll have x plus 1 equals -2y. And last step, we can divide both sides by -2. And if we rewrite our answer in y equals form, we'll have y equals, we can have a negative outside the fraction, and x plus 1 over 2. So the inverse is y equals -x plus 1 over 2. To write this in proper notation as a inverse, since y was originally equal to -2x minus 1, instead of the final answer being y, this will be the inverse of y, which we can write as a -1 exponent. So y to the negative first power is the inverse of y equals negative x plus 1 over 2. Second question, and last question for the section. F of x equals x minus 5. Instead of a y for the function, we can have f of x equals. To find the inverse, we can first take f of x and replace that with y, since the function of x is similar to being the y value. If we write this as y equals x minus 5, it's the same function, and now we can take the inverse. Switching the x and the y again, we'll have x equals y minus 5. And last step, we want to solve for y. We can add 5 on both sides. And if we write the y on the left-hand side, we'll have y equals x plus 5. To write this in proper notation, since we started with f of x, we want our answer to be in f of x form. So we can put f, and adding a negative 1 exponent would be the inverse of f. So f to the negative 1 of x equals our answer, which is x plus 5. So our final answer, the inverse of f, is equal to x plus 5. Title of the last section today is Determine. If the pair of functions are inverses. In this section we'll have two functions, and we'll determine if both functions are inverses of each other. The definition for the section: inverses. If f composition g of x is equal to x, and if g composition of f of x is also equal to x. So for the section, if you take both compositions of the two functions, if they're both equal to the x value, just a single x, then they are inverses. If one or both is not equal to x, then they're not inverses. First question, f of x equals 2x plus 8, and g of x equals 1/2 x minus 4. To solve this again, we'll take both compositions, f composition g, and also g composition f. If we take the first composition, f composition g, and again from previous sections, we'll start at the right hand side, we'll take g, and we'll plug that into f. So the g function, 1/2 x minus 4, we'll plug that into the x value for f. So f of x would be 2, but instead of x, we'll plug in the g value, which is 1/2 x minus 4, and the rest of the f function has a plus 8. Simplifying this, and again if there's inverses, we should end up with a single x. 2 times 1/2 would cancel out, so we'll be left with x. 2 times a negative 4 would be negative 8, and the plus 8 left over. Negative 8 plus 8 would be 0 or cancel, and we'll be left with x. So the first composition is equal to x, and if we check the second composition, if it's equal to x, they're inverses. If it's not equal to x, then they're not inverses. The second composition, again, will be g composition of f. Again, this time we'll take f, the function, and plug that into the g function. The f function again is 2x plus 8, so we'll plug that function into the x value for the g function. So the g function starts with 1/2. Instead of x, we'll plug in 2x plus 8. And the rest of the g function, it has a -4. Simplifying, 1/2 of 2x would just be x. 1/2 of 8 would be 4. And 4 minus 4 would cancel or be 0, and we'll be left with x. So since both compositions were x's, the question is determine if their pairs are inverses. The answer would be yes, they're inverses, since both compositions are equal to x. Second question, and last question for this section. The two functions, f of x equals 3x plus 4, and the second function, g of x equals 3x minus 4. And again, we'll take both of these functions, do both compositions, and if they're both equal to the single variable x, they're inverses. If they're not equal to x, then they're not inverses. The first composition again we can do is f composition of g. And again, we'll start at the right side, take g, and we'll plug that into f. So we'll take 3x minus 4 and plug that into the variable for the x. So we'll have 3, and instead of x, 3x minus 4. And the rest of the f value will have plus 4. Simplifying from here, 3 times 3x would be 9x. And 3 times a negative 4 would be negative 12 plus 4. And simplifying, we'll have 9x minus 8. Again, for these to be inverses, when you do either inverse, it should equal to x, just a single x, and not 9x minus 8. Anytime you get something different than x, the answer to the question would be no, these are not inverses. We don't have to do the second part of the problem. Since the first inverse is not x, then they're not inverses. Title of the first section today is Graphing. Square root functions and state, domain, and range. In this section, we'll graph square root functions and we'll state the domain and range of those functions. One definition that we'll use for this section is start when square root equals 0. For the section where we graph using t-tables, we'll start the t-table when the square root is equal to 0, since the smallest value a square root can be will be 0. First function we'll graph is y equals square root of x. To graph this again, we can use a t-table. For a t-table again, you can use any sets of numbers that you want. The best sets though, looking back at the definition, is we'll start the table where the square root is equal to 0. If we have a single x inside the square root, that means the square root equals 0 when x is equal to 0. And for the t-table, we can do a couple numbers past that to get the graph for the function. If you plug a 0 in, square root of 0 would be 0. With a 1, square root of 1 would be 1. And plug a 2 in, the square root of 2 would be square root of 2. Graphing this on a xy axis, 0, 0 would be at the origin, 1, 1, and 2, square root of 2. You can either use a calculator to get the decimal, or you can estimate the square root of 2 would be a little bit above 1. We'll end up with 3 points. These 3 points make a curve, and if we extend that curve out, the square root function will basically be a parabola shape, but with only half of the parabola. The negative parabola won't be on here, since if we had the negatives, this would not be a function, as it's not one-to-one. But the square root function shape is a parabola going sideways, but only half of that parabola. Second part of the function, we want to find the domain and the range. If you remember from previous sections, the domain are the x values and the range are the y values. Looking at the graph, the x values, the smallest x value we can use is also the definition that we started with. So the smallest x value would be 0. Anything less than that would give us an imaginary number. So the domain would be x is greater than or equal to 0. For the range, we look at the y values. The smallest y value on the graph would be 0. We won't have any negative values on here, since we can never take a square root of a number and get a negative. So the range will also be y is greater than or equal to 0. Second question and second function we'll graph. Y equals the square root of x plus 4. Again, graphing this, we can use a t-table. And again, to decide which number to start at, we can look at the square root, or the function inside of the square root, which is x plus 4. And we want to start the t-table where x plus 4 is equal to 0. And that value would be negative 4, since negative 4 plus 4 would be 0. And again, you can do a couple numbers past negative 4. We can do negative 3 and negative 2, so we get the correct shape for the graph. Plugging a negative 4 in, negative 4 plus 4 would be 0, and the square root of 0 would be 0. Negative 3 plus 4 would be 1, and the square root of 1 would be 1. And negative 2 plus 4 would be 2. Taking the square root of 2, we can leave that as the square root of 2. Graphing these on a xy axis again. The first point is at negative 4, 0. And negative 3, 1. And negative 2, square root of 2. And again, square root of 2 would be a little bit above 1. If you wanted to, you could do more points, but again, the shape will be a sideways parabola without the bottom part of the parabola in these graphs. For the domain and range again, we can look at the graph for the xy values. The smallest xy value on here would be negative 4. Anything to the left of negative 4 again would be imaginary numbers. So the x values have to be greater than or equal to negative 4. For the range, the y values, the smallest y value on the graph, again, is 0. And again, we cannot have any negative y values since we do not have imaginary numbers for this graph. So y has to be greater than or equal to 0. And last functional graph for this section is y equals negative square root of 2x plus 1. Again, graphing this, we can use a t-table to determine which number to start at. We can look at the square root, or the function inside the square root, which is 2x plus 1, and we want to find out where 2x plus 1 would be equal to 0. If you want to, you can take the equation and set it equal to 0 by subtracting 1 on both sides and dividing by 2. We'll have the value of x equals negative 1/2. So if we start the t-table at negative 1/2, then we can pick a couple values above negative 1/2 to get the graph for the function. Above negative 1/2 or bigger would be 0 and 1. Solving for the y values, if you plug in negative 1/2 into the function, 2 times negative 1/2 would be negative 1, plus 1 would be 0. The square root of 0 would be 0, and negative 0 would still be 0. Plug in a 0 into the function. 2 times 0 would be 0, plus 1 would be 1. The square root of 1 would be 1, and the negative outside would make the y value a negative 1. And plugging a 1 into the function, 2 times 1 would be 2, plus 1 would be 3. We'll have the square root of 3 with a negative outside, which would be negative square root of 3. Using these values again, we can draw the xy axis to graph the square root function. The first point would be at negative 1/2, 0. Second point would be at 0, negative 1. The square root of 3 again will be bigger than 1, but it'll be less than 2, since the square root of 4 would be 2. And it'll be negative, so in between negative 1 and negative 2. Looking at the points this time, the points line up to make a curve, but the curve this time will be going down instead of up. The reason for that is if we have a negative outside the square root function, the negative makes the square root function go down. And last part of the question, to find the domain and range. The domain again are the x values, the range would be the y values. Looking for the smallest x value in this function. The smallest x value is where we started the t-table, which is at negative 1/2. So all the x values have to be greater than or equal to negative 1/2. And the range, the y value, the smallest or critical y value is at 0, but this time the y values go down, including the negative numbers, but they do not include the positive numbers. So that means 0 is the maximum point. There is no y value positive, so that means the y values have to be less than or equal to 0. Title of the last section today is Graphing, Square Root, Inequalities. In this section we'll continue to graph square root functions, but instead these will be square root inequalities. First inequality we'll graph is y is greater than or equal to the square root of x plus 5. To graph this, we could use a t-table like we did before and graph the points. Or if we want to, we can find a single point and then graph the inequality. For example, if we draw the xy axis graph, the single point that we want to graph is where the square root is equal to 0. In this case, x equals negative 5, the square root would be equal to 0. So we can graph a single point. The x value is at negative 5, and if we plug in negative 5 in, negative 5 plus 5 would be 0. The square root would be 0, so the y value would also be 0. Using this single point, this point's where the square root function starts. And if looking back at the previous graphs, the square root will either curve up to the top or curve down to the bottom. In this case, since it's a positive in front, there's no negative signs, the square root will curve up to the top. It is also a solid line since it's or equal to. And the last part, since it's an inequality, we have to shade either above or below the graph. In this case, it's greater than or equal to, so we'll shade above the graph. When shading square roots though, we cannot go past -5. So to the left of -5, neither the top or the bottom will be shaded. But starting at -5, going above the graph will be shaded for this function. Second question and last question for the section. We have y is less than the square root of 6x minus 2, and outside the square root plus 1. And again, if you wanted to, you could do a t-table with several values to graph, or if you find the one point where the square root starts, then we can graph the function from there. To find that point, we want to find out where the square root is equal to 0, or where 6x minus 2 equals 0. Solving it for 0, we can add 2 on both sides. So 6x is equal to 2, and dividing by 6, if we reduce fractions, the x value we'll use is positive 1/3. So graphing the function on the xy axis graph, the x value will be at positive 1/3. So in between 0 and 1, the y value, to check if it's at 0 or a different point, we can plug it back into the equation. Plugging a 1/3 back in, 6 times 1/3 would be 2. 2 minus 2 would be 0 for the square root. The square root of 0 would be 0. Adding 1 to it though will make the y value at 1. So our x value is at 1/3 and the y value is at 1. Graphing again, the square root will either curve up to the top or down to the bottom. If there's a negative outside, it goes down. Since there's no negative, it curves up to the top. It is an inequality though, which is less than. Since it's not or equal to, it'll be a dashed line for the inequality graph. And shading either above or below. Less than will shade below the graph. Keep in mind though, we're not going to shade anything to the left of 1/3. So imagining a line going down 1/3, we'll shade everything below that and to the right. And that would be the graph for the function. Title of the first section today is Simplify Radicals. In this section we'll simplify radicals, which is the same as simplifying square roots. First question, we have the square root of 1/16. When you have a square root of a fraction, if you remember, you can take the square root of the numerator and also the square root of the denominator. The square root of 1 would be 1, and the square root of 16 would be 4. So our final answer, the square root of 1/16, would be the square root of 1/4, or 1/4. Second question will be the cube root. A cube root will be a radical or square root sign with a 3 on the outside and -27 on the inside. A cube root, instead of a number times itself that's -27, we want a number times itself 3 times, that's -27. Thinking about a number times itself 3 times, that's 27 or -27. If we take the number 3, 3 times 3 times 3 will be 27. And if we make it negative, -3 times -3 is 9, times -3 will be -27. So the cube root of -27 would be -3. If you remember from previous sections, we cannot have a negative square root, otherwise that would be imaginary numbers. But for a cube root, we can have a negative cube root, since 3 negatives multiplied would be a negative. Next question. The fourth root. The fourth root again would be a